Right. Hello, everyone. I'm really excited to introduce David. David's from McGill, where he is also part of an organization that is centered on trying to help build interest in research in artificial intelligence. So he's currently a student in CS at McGill University, like I said, and he's also a research intern at Microsoft Research in Montreal. His current research resides at the intersection of natural language processing and reinforcement learning, and today he'll be talking about using reinforcement learning to beat text-based games. So hand it off to you, David. Thanks.
Thanks, Dan. So yeah, as he said, my name is David. I am a Singaporean McGill University student, currently studying CS. Yeah, and I'm also the president of the McGill AI Society, big shout out. And I'm also a research intern currently at Microsoft Research Montreal. And I, as you said as well, I mainly deal with NLP and the intersection of NLP and reinforcement learning. So yeah, that was a quick intro about myself. Let's get started. So first off, what is the text-based game? Actually, what I've tended to notice when I ask this question to a lot of people, a lot of older people or a lot of people that like to hack around with terminals and stuff know more about text-based games than people who don't. So text-based games are basically just games that you play on your computer that you type in the command. They'll tell you like a quick description about like the current environment you're in. So for instance here, you're in a bedroom, you can see the chest drawer, you idly wonder how they came up with the name TextWorld. It's pretty fitting, blah, 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 and it basically describes your world to you. And what your task is to find a command to do, maybe to change the state somehow, pick up a key, do a set of actions until like you reach a certain end goal. And that end goal could be anything from like cooking a carrot, which we'll see later, or like eating an apple or something. So many of you might be familiar with the game Zork. That's a really popular game that a lot of people in the text-based game world really know a lot about. It's actually one of the first ones too that came out. And it's this huge, elaborate game that like, honestly pretty hard for a human to beat. But we'll talk a bit about like different methods that people use and different things people do to try and beat these games. So before we get started on like techniques we use to beat these games, first off, let's talk about why we actually want to beat these games. Why do we care about text-based games? They're outdated. Why don't we try and beat, I don't know, Dota instead, like OpenAI 5 or something, right? So there's actually a lot of research opportunity behind text-based games. The first one is it's very simply a very simple version of a text environment. And what do I mean when I say text environment? That could be anything that could be something like a dialogue system or even anything that relates anything in the real world to text. So basically we can model our environment with this text and we can learn from these interactions between different entities within our text. There's actually a lot of common sense understanding in text. So a perfect example of this is like, I know that I can hold a microphone, right? I know that I can speak into a microphone. All of these entity relationships, they're actually very hard for a machine to understand. And it's actually very easy for us to understand. A perfect example of this is if you guys are interested in common sense reasoning and common sense learning, is the Wintergrad Schema Challenge. It's actually it's a challenge that Nuance Communications released a while back, and it's basically supposed to be a replacement for the Turing test. So it's supposed to be a replacement to see whether machines actually understand, can actually converse with a human. So I'm just going to go into quick divergence into it because I think it's a really interesting problem. It's basically a data set of 100 questions. And there's simple binary answers to the question. So it's either one option or the other. And so, sorry, forgot to mention, if you guys have any questions during any time in this presentation, please raise your hand. I'm more than willing to answer it. Also, yeah, so back to the Wintergrad Schema Challenge. You basically have questions like, you try and put the trophy into the suitcase, but it was too big. So what does it refer to? So in terms of this, for us, it's super easy to understand that, oh, it is obviously the trophy because it's too big, we can't put it into the suitcase. But if you actually think about what goes into understanding that context, it requires a lot of reasoning and understanding that we've learned throughout the years since we were very young. Sorry for the divergence. Just wanted to prime you guys up as to why we're doing these things. So one other thing that we might want to, like I said before, a text-based game is basically a glorified dialogue system, right? So we're basically talking to this game. We're saying, oh, go east, and it'll reply you. It'll give you a reply, something along the lines of, oh, you walk through the east door, whatever, whatever. And so in this way, we can frame it as a dialogue system, and this could also be useful for dialogue problems. So let's start off the challenge that we're trying to beat. So this is what I call the carrot cooking game, and it's a very simple challenge that we formulated with the TextWorld framework. It's a text-based game framework that's very similar in the API reference to OpenAI Gym, and it's basically an environment that allows you to train an agent of some sort to very similarly to how you would train an OpenAI Gym agent. So yeah, this is a framework created by Microsoft Research in Montreal. I actually worked on it over the summer, so just weird flex. And also, if you're interested in the framework, it's on the Microsoft website over there. You can go check it out. So the game that we're trying to beat is a very simple 13-step game. So we start off in the bedroom. P means player, right? We have to pick up the old key from the chest drawer, unlock the wooden door with the old key, open the wooden door, go through. We basically navigate through to the garden here. We pick up the carrot here, and we go back to the kitchen where we put the carrot on the stove, and then we cook the carrot. So that's a very simple game. The commands consist of like 2 to 5 length phrases of like, oh, go east, pick up carrot, and you're expected to type these things out normally. So we're looking to build an agent to try and beat this. This is one example, but beat this archetype of game. So they're very simple. TextWorld produces very simple games that that allow you to they produce very simple games that we use in order to try and give our agents a better chance at understanding language. So what are some challenges with text-based games? So for you and me, it might seem really easy. Oh yeah, I can like open the door and whatever. But if you actually think about this in terms of a text generation problem, it's actually not an easy problem. And if we frame this in a reinforcement learning context, you slowly start to realize that it becomes quite a big problem. So first off, let's start about the natural language state space. So natural language, as we all know, is like exponential in nature, and you can do so many combinatorics of words and stuff in order to produce different meanings. So we need to encode that down for a model or an agent of some sort to understand. Another really hard challenge with these games is that, so let's say, let's go back a few. So if we see this room description, like, right, you're in the bedroom, you see a chest drawer, blah, 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 blah. If we see here, there are multiple entities and multiple things you can do with those entities in the room. So every different state, and when I say state, I mean one of these rooms that you're in, I guess, you have multiple actions that you can do. And your traditional reinforcement learning tasks, most of the time, they have a fixed number of actions you can do, and then you find a probability distribution over that if you're doing some kind of policy learning, whatever. We'll talk about that soon. But this is a very big problem because we need to somehow deal with the fact that we have a variable number of actions, and also the number of usable actions, like I said before, we'll call those admissible commands. So an admissible command is something that will actually change the state and not just do something random. Like if I say, oh, eat the carrot, but there's no carrot in my inventory or there's no carrot in the game, that's not going to do anything, right? It's useless. So when we say admissible, it means something that will actually change the underlying state. So we need to somehow find the correct action within these admissible actions. And finally, another big challenge is understanding the relationships between the entities. So there's a lot of work that goes into like entity relations. Recent ones that came out, I guess, is like the neural knowledge language model that uses like predicate calculus-ish kind of like graph network in order to represent relationships. But yeah, we basically need this contextualized common sense understanding, and we argue that this environment and learning from this environment is a step towards that. So let's talk about some possible solutions. This is all ongoing work, so we're still formulating. We do have some results, but most of it is us just trying to understand the underlying problem and thinking about smart solutions for them. So one of them is just hand engineering modules to solve these text games. So there is a group from, I think, Microsoft Research Redmond that recently won the interactive fiction competition. That's a yearly competition that goes on that, like, you basically get a test set of games and you have to achieve as many points as you can within that game. And so they managed to do very well. They managed to win this year in 2018. And, but their solution is basically a hand-engineered solution that basically says, oh, if you see this in the state, then you should be in like fighting mode. Or if you see this, you should be in navigating mode. If you see this, you should be in exploring mode. So it's not very robust, and it's static, and it never learns from its environment like we would like it to. Another approach, and the approach that we're going to be talking about today, is using model-free reinforcement learning. So this can be categorized generally into two things: off-policy methods and on-policy methods. Obviously, this is also true for model-based, but yeah, we'll be focusing on mainly the on-policy methods, and we'll get into that real soon. And finally, model-based reinforcement learning. This is a very exciting part of what used to be part of control systems, but now people are starting to revitalize their interest in this. And they're looking to combine the methods that we use for model-free and model-based reinforcement learning in order to have better sample efficiency and lower variance, pretty much. There's a great paper out by David Ha, who does a very nice baseline of where we are right now with model-based reinforcement learning kind of thing. And I'd highly recommend if you guys are interested in looking at that. So yeah, let's talk about the approach that we are arguing for. So the approach is we basically have some form of text generator that can generate multiple phrases. So it's not just your simple text generation where you just generate one single sequence. We want a variable-sized number of phrases. So we generate the set of actions, and what we do is we feed this into a command selector or a policy. And this command selector, or our policy in this case, will spit out actions or action probabilities, as most frameworks do. And we sample from this, we feed it to the game environment. Game environment gives us back a state, and we go on and go so on and so forth until we either reach the end or we fail or something. So let's break this down a bit first. First, let's talk about the action generation. So let's talk a bit about how we can generate words that we've never seen before. So this is a problem that has come up pretty recently. Well, I guess 2 years isn't very recent in deep learning. This is a problem that has been actually kind of solved in the past years with what are called pointer networks. And they're basically your typical encoder-decoder networks, except your decoder, yes, it also uses attention, but it learns to generate either a word at your given time step, either a word in your context, or a word in some given vocabulary. So this is actually a really powerful concept, because what this enables you to do is to have some form of text generation that will pull things from the context depending on how much it needs it. And so we leverage this because we want our model to pull entities from the context and to use these entities in the actions that it generates, right? So this is what's called the pointer softmax model, and there's a great paper called Pointing to the Unknown Words that you guys should definitely check out if you're interested. And it basically comes from this whole using the attention mechanism to decide, and also having this switch that basically decides, okay, at this time step, do I want a word from my context words, or do I want a word from my vocabulary? So it manages to slot in these values and give you very robust and decrease the number of unks, unknown tokens in your generation. So yeah, I'm not gonna really explain all of this. I mean, this is basically what we were saying. You're at a current state. This is your switch. You decide whether to generate something from your vocabulary or generate something from your a context. And the context in this case is just like our encoded representation of our context. Yes. So yeah, this is what we do to generate a single action. But we still have the problem where we need to generate a variable number of actions per given state. And so there are a lot of different approaches to this. Our initial approach was to basically have use this, and in order to increase the number of actions we generate, we just basically use beam search. And I'm not going to go into beam search. If you guys are interested, come talk to me afterwards as well. But what beam search does is it follows a beam of highest log probability, and we take like the top k of those actions generated. So we take the top, let's say, 10 actions that it generated, and we would feed those actions into our model and go from there. But what happens here is because we don't train with this beam search objective, you tend to generate like a lot of noise. And when I say a lot of noise, I mean like a lot of noise. So this approach wasn't great, and the larger the action space for our command selector, the worse it'll do, purely because it just has so many things to look for. And as we all know, softmax over a large vector space will pretty much do nothing for you. So what we can do instead is leverage a technique that's called hierarchical recurrent encoder decoders. It's called what I'll call HRED. It's a paper that came out in 2015, and basically what it does is you have your encoder here still, like you do your normal sequence to sequence. You also have your decoder here, but what you do in between is you put an LSTM or some RNN of some sort that remembers state between the two. And so what this does is it allows you to generate multiple time steps. So sorry, this is just me doing crude drawings because this is the picture from the original paper, but basically what we do is since we only have one, normally what this is made for is a dialogue system where like you would have a query, this is called a query, and it would give you a response. You would get another query because it's a dialogue system, answer response, and you would get another response. But our basic technique is, we don't need this second state, so we can plug in this context from the second one into here. And yeah, that's how we leverage hierarchical language modeling. And it actually tends to do pretty well. We are assuming in this context that the sequences of actions that we generate are sequential in nature and they're ordered. Whereas if we actually look at the actions we actually care about generating, we don't really care if we generate eat carrot first or cook carrot, right? It could be cook carrot and eat carrot. So we still haven't found a reliable method to get around that. And set generation itself is actually it's a very hard problem in text generation. So yeah, we use this hierarchical nature in order to generate diverse set of words, and it actually prevents, what we saw in the model is that it actually prevents similar actions to be produced, which is a good thing, right? And just to get some context as to what our data set looks like for this supervised portion of our training is we have the state description here. We also condition on an entity to tell it, oh, you should look at this entity in your action. We can also use it without. It actually works pretty well as well. And we basically have a set of target actions that we want to generate. So basically, in order to put everything together, we would feed this state into the encoder here, right? We'd feed it through, and we train on cross-entropy loss between this and the first action, which is closed type G-safe. And then we expect it to generate on the second one, this second action, and so on and so forth, until we generate everything, until we generate a stop token, which is very much what you normally do in text generation. So now let's talk about the control policy. I'm sorry, this is all very technical things, but the techniques we use are pretty cool, I think. So we actually use a variation of advantage. Actually, it's asynchronous advantage actor critic because TextWorld allows us to do batch training. And what we do is we have our encoded representation from here, right? We feed this into some other, another RNN of some sort. We also encode the actions that were given in. We encode these actions with the same weights, and what we do is we do attention over the actions. So if we go back to our actions, we basically do attention over these actions with this as our value in order to get a distribution over these actions to know what to pick. So once we have a distribution over these actions, that's basically what a policy gradient is, right? We now have a way of giving us our policy gradient, and we basically train on using policy gradient methods, or in our case, advantage actor critic. We also have a separate head for, this attention mechanism that gives us a value approximation, which is what we do in advantage in actor critic. And we do this in order to decrease variance. And we see that with all of these things combined, we currently are only training separately our generator and our action selectors. So in future work, we're actually looking to incorporate some other methods. So currently, we are writing up a submission for our NIPS workshop. Actually, let me do that first over here. We have a 2018 NIPS workshop on specifically text-based games. So if you guys are interested in learning more about text-based games and learning more about how you can leverage text-based games in order for language understanding, I would highly recommend you check out the website, wordplay, 2018.com. And basically, if you're in NIPS, please stop by the workshop. There will be more. We're actually releasing, well, the team is, I'm not part of the organizing team, but the team is releasing some text-based game competition with actually a harder problem than your normal carrot cooking game. We're a bit skeptical whether people can actually solve these games because we've seen that they're pretty hard to solve. But yeah, it's very exciting. We're going to see a lot of results. I would have, and let me talk a bit about the results that we've seen so far as well. I don't have a slide for results because this is, as I said, ongoing research. We're still collecting results. But with our sequence generation, we do see a decent diversity in all of our actions. We get pretty good accuracy as well. But the only problem is if you have static generation and a policy that tries to learn from static generation, if you don't produce the action that's required to beat the game, then you're screwed, right? Because you're never going to find the action that you need within the list of action that's given. So this is a big problem we're also trying to solve in our ongoing research. We're also considering prioritize experience replay in order to look back at good experiences and learn from those. We're also looking at one time we're also looking at model-based reinforcement learning, but that's still ongoing. And also, we're also looking at a subtask for our agent to try and answer questions based on the encodings that it's seen so far. So let's say it's seen like a table, and it keeps going on. What we potentially want to do is later on ask the agent a question like, where was the table what room was the table in? And it would hopefully spit something out along the lines of, it was in the bedroom, right? So this is just another way of validating that our model is actually learning these proper entity relations instead of just overfitting, basically. And yeah, if you guys have any questions, I think that's it. Thank you. Yeah.